this computer. Okay, so as always, thanks everyone for joining us today. Today is the day 6, so it's so we have been having some classes and some effort, and I think we are almost finishing the SER part, at least the basic part. Then we will move to the parallel wrap. But I think today it's something that we use SER for doing it, but it's not strictly a SER procedure, but I think it's very useful for almost everyone. And I think it's interesting because as MHD simulations, they are evolving. I think more and more we will use them as a lab or as a reference parameter to test our codes or our computations or our assumptions. So I think being able to transform simulations to then use it for synthesis is something that I think is useful, and we will do more and more. So then today's class is to transform a given simulation, 3D MHD simulation, to use it with SER. That it means that we can also use it with Desire. We will use an extra routine from SER. It's not the main code. It's a new one called Modelador 3 in this case. So then you need to compile it in the same way as you compile the SER main module. You just type make. If you have the Intel compiler, you don't need this. But if you have, for example, G-Fortran, then you just put it like this. And then you type the routine and with the X extension. So then the code will read the F routine inside and then will compile a new one. So then you will have a new executable that will be called. I will tell you how to call it later. But this is a new executable that is not the same one as the main SER executable that we use for synthesis, response functions, or inversions. Okay, so then the steps that we need to take for transforming simulation is to put it in a specific format. And by that means specific units, a specific convention of signs and other things. I will show you how to do that. And then we will run the code. So the idea is that we will start from a combination of temperature, gas pressure, and geometrical height. And from that, we will run this Modelador 3 to compute a combination of temperature, electron pressure, and optical depth at 500 nanometers. Okay. And just as a warning, I think the problem is background opacities, but if not, Basilio will correct me. But the idea is that this program, when you run it, it will work. So I mean, the optical depth that you will compute, it will work if you are under 10,000, 15,000 Kelvin. If you start to get to hotter layers, then the computation will fail, or yeah, in general, will probably not be correct. So then we will have to use another method. But before that, maybe Basilio has something to add.
No, is that, yeah.
Okay.
It's, the limit is 20 Kelvin, 20,000 Kelvin, but over 15, the results are not accurate enough. Yeah.
Okay. So then what I want to say in this case is that just transform photospheric simulations or the photospheric part of the simulation with this method. So mainly for using it with photospheric lines. And then if you want to analyze chromospheric spectral lines or do synthesis with chromospheric simulations, then we will cover that later on when we start using RH. We will tell you how to compute in a similar way like this one. So to compute the optical depth, so then you can use it for synthesis or inversions in non-LTE, including chromosphere. But today is for the main for the photosphere mainly. Okay, so then we will first learn how to download the simulation and how to put it in a proper format. I put the web page here, but I will show you now how it looks, but then you can copy it from here. I think I also put it yesterday in the mail. and then we will transform it to search format. Okay, so this is the first part. So then this is how the web page looks. This is inside a HAO web page. So you have several options. So you have a README file and also here. So then you can understand more or less what the different files are. And you have 3 versions. So this is the full sunspot, like this one, with a lower spatial resolution. So the spatial domain is, so I mean the over the surface is 32 times 32 kilometers, and the vertical, I mean not domain, the step is 32 kilometers, and in the vertical domain, the step is 16 kilometers. Then, so and you can see that it's relatively heavy, but not so much. So each atmospheric parameter, it's the atmospheric cube, it's 1.12 gigabytes, so it's not so bad. And then you have the full sunspot, the same one as before, but with a much higher spatial resolution. So this is 12 kilometers in the spatial domain and 8 kilometers in the vertical domain. So this is very close, well, depending on the wavelength, but it's very close to the spatial resolution of the KIST at 500 nanometers. But here you can see that each atmospheric parameter is already 16 gigabytes. So it's a bit heavy, although I think it's worth it to use it later on. But for today, we will use this one because it's easy to visualize things and to run on the computer. But later on, depending on your targets and your interest, you will pick one or the other. But they are basically the same one, just with a different spatial resolution. And then you have a third one that I think is also interesting because is the previous one, but just a cut, a horizontal cut of the full field of view. So it's just that if you want to try this high spatial resolution with some quiet sun, some penumbra and some umbra, you will have it here, and it's much lighter, so it's not so heavy. So then if you want to try the same things that we will do today with a high spatial resolution, you can start with this one. And then if everything works, or if you think that this is the simulation that you want to use, then you can download this one. But they are basically the same one, just with different spatial resolution between these two and different field of view between this and this one. Okay, so if there are no questions so far, then let's start. Sorry. So we will have 2 folders. The first one is this one called Miran Asir format. So there I just have this procedure that we will go through it. And this is something that we will produce today. But this one, I will put it in Dropbox. So it's okay if you don't want to run it, you will have it also. And this is something in case you want to use IDL and you want to do the same plot that I made. This is for loading a color table that contains blue, white, and blue, white, and red color. But it's not necessary. I just put it here in case you want to use it. So then let's start with format. As I said, we are going to start with the Muram simulation. You can download it from here. I will not put it in Dropbox because as you can download it, and then we don't need to put it in Dropbox. But all the products that we generate today, I will put them in Dropbox. So you don't need to run the programs. Yes, if you want to check what I did, you can read it from there. So this is just something that I put the simulation there. So you put it somewhere. And then this is something that is in the README file. So the simulation in the low spatial resolution, it's a simulation with, in the spatial domain, in the horizontal domain is 1,556 pixels. And in the vertical domain is 120x pixels. And just as a reference, I put it here, the pixel size of each one. So then just let's start reading. So we will read the temperature. We already have the dimensions from before. So then we read the file that we can download from the web page. And then after just reading it, this is something that I do, and I think is required for SER. So the Muram simulation in general, they have that. Let's go to the web page. We're here. So if you see, they said that the pixel size is 32, 16, 32. And the idea is that if we count these dimensions, so if we said that this is X, Y, and Z, so the way they save the rise is that this is the one horizontal domain, this is the vertical domain, and this is the second horizontal domain. So then the first thing I do is I transpose the atmosphere, the atmospheric parameters. So then now the temperature that we have is X, Y, that is the horizontal domain. And then the third dimension is the height. That is the one I usually work on, and I feel more comfortable in this way. So just be careful that if you assume that it's like that, then be sure that you are transposing. If you are using, for example, Python, then be sure that you are transposing and everything looks okay. So then I put a stop here. So what I'm going to do is to check that the temperature looks reasonable after doing this transformation. And then before I already checked just by visual check how the granulation looks, trying to find some height where, so some region where we assume that the height could be set equal 0. I mean, it looks like granulation. And this is the pixel 80 from the vertical domain. So what I'm going to do is going to plot this temperature at a fixed height and all the arrays just to check that it looks like it should be. So if I do this, and then this is how it looks. Okay, so then it means that the transformation that I did, it looks okay. And this, it seems that it could be set equal 0. I mean, the optical surface. So we have granulation, we have the sunspot, and we have the penumbra and umbra. Okay, so then we can continue. In this case, we will need to have a geometrical height for do the transformation. It's not provided by the simulation. So then I decided to define one, and I'm setting that again, pixel 80 will be like 0. So just to have an idea more or less of the vertical domain that we cover with the simulation. But the truth is that for the transformation is not really important, but it's just to have an idea of how deep the simulation goes or how high, just in case we need to cut it later. So just let me run this. So the stop, okay, so then I do this. So then if more or less this vertical domain that I define is correct, then we can check that the simulation goes from around minus 1,200 kilometers up to 700 kilometers. So then we go a bit deep, but I think it's important because we have an umbra, and so then things, it's important that we reach deeper layers. And then we go relatively high, so 700 kilometers, I think is still fine. So then the code in principle should work in this range of heights, because it's still, we are probably around 10,000 Kelvin, something like that. So then we now have to do the same with the other atmospheric parameters. So we define the gas pressure and we read it. And again, we transform it to keep it as X, Y, so I mean horizontal domain and height. And then we do the same for the velocity. So just let me remove this one, this one. So let's run it again. And then I'm plotting the velocity here. So last 1 second. And I'm plotting just a cut. So as I said, the full domain is 1,500 pixels. So I'm just plotting a part of granulation. And the idea is that I'm doing this because if you see what I have done is the same process as before, then I make the transpose of the original, but then I also multiply by -1. And this is because the sign convention for the simulation is the opposite that we use in SER. and I think it's called Spectroscopic Convention. And then what I'm doing is to check that we have the proper convention. So the idea is that if you plot granulation and you have a color table like this one, so I mean blue means negative and red is positive and white is 0, then the pattern should look like this. So then intergranules, that are the narrow lanes, they should have a positive velocity. So it should be a downflow respect to the surface. And then granules should be with the opposite sign and in blue, or with negative velocity. So if you see a different pattern, then you need to change the sign, because this is important for SER, because otherwise then you are mixing things. As always, before I forget, we have the high quality figures. So for example, this one, it's already here. So then you will be able to check it, and also the one for temperature. So even if I'm showing you here, then you will also be able to see it in high definition. So then let's go back to the program. So now we go to the magnetic field, and again, so in this case, BX. So I just do the same process and I load this one and then maybe transpose. But in this case, BY, it's changed. So be careful about this. So I'm defining BY, but I'm reading the Z component, because I want to have X and Y to be the horizontal component of the magnetic field. And then in the case of the line of sight component that I want to define, it's the Y label in the simulation. And just to be sure that this is correct, so I just plot it here. I will show you how the program runs, but then we will go to the high quality figures. But just, so this is the new BX that I have defined at the same height. So what I believe is Z equals 0 kilometers. Then this is the new BY that you can see similar as before. And then this is the new BZ. So just to be sure, I made the, I think, so this is this one. So after that, after doing the transformation, this is how it looks. So then you have that BX, it looks like this. And then as the sunspot is symmetric, then BY, that is the other horizontal component, is essentially the same, but rotated. And then you have that BZ. Now it's what we always assume as longitudinal magnetic field. So then here we can be almost sure that we have done the proper transformation, and now we have that BX, BY, and BZ are what we want to have as BX, BY, BZ. Okay, so then the next thing we need to do is that these are Cartesian coordinates. SER and the side, they work with spherical coordinates. So then we need to make the transformation. And in this case, yes, I will do it already because it takes like 1 minute or something like that. So then I just define the modulus of the field strength, the inclination, and the azimuth. And then I run a loop. And then I'm computing the modulus as the square root of the 3 components. And then the inclination, you have different ways, but this is one way. So it's just the previous modulus, and so BZ divided by the previous modulus. And then the azimuth is the tangent of the BY and BX. So this is ideal nomenclatures. Probably if you use a Python, you have your own routines. But the idea is that later I will show you how it looks, and just to be sure that it makes sense. And the next thing that we need to do is that the values those routines provide, as is in IDL, they are in radians. So then you need to change them to degrees, because it's the values SER needs. So then I'm just dividing by this degree to radian routine. So then you have everything in degrees. So I'm just running it just to show you that the transformation is really fast, so it will take no time, but we can go to the figures already, so we can check how it looks. So this is now the modulus of the magnetic field, that it looks like the longitudinal component, but now it's just always positive. Then we have the inclination that it's saying that it's very vertical in the center of the umbra, and then it's getting horizontal. This is 90 degrees in the penumbra. And then in outside, you can have everything, but you can see that these dark patches, they correspond to vertical magnetic field, and this is what we had before. And then you have azimuth that it's, again, as it's radial, then it's just turning around. So it's a very nice sunspot. And then outside, it's a bit complex. But basically with this, if you plot this and it looks like this, then you can also assume that the transformation seems to be correct. Okay. So then after that, I put a stop here. Yes, so then it already finished. So it's relatively fast. You can do it over the full field of view. So then up to this point, we have everything we need for SER. So we have temperature, gas pressure, geometrical height, velocity in the proper sign, and then the three components of the magnetic field in spherical coordinates. Before I forget, so the simulation is already in CGS. So then we are not changing units. But sometimes when you have a simulation, for example, from Bifrost is SI, so you need to change to CGS. Or if there's another format, then just be sure that you need CGS for SER, and the geometrical height goes in kilometers, but the rest of the parameters, they go in CGS. Okay, so then at this point, we could save those values, and then we can just try to run the program for computing optical depth. But what we are going to do now is an extra step, that is to save them in the proper format to just have it ready for running in parallel in the future. So it's something similar as we did in the previous class. So then in this case, you could do it for the full field of view, but just for simplicity, I'm going to pick just 250 times 250 pixels. So I define these, and the dimension is these, the difference between these two. And the idea is that you could also reduce the vertical domain. So imagine if the simulation goes up to, I don't know, minus 3,000 kilometers, and you are not really interested in something that is happening there, or you don't have a very strong depression. So maybe you could reduce to minus 1,000 or minus 1,500 kilometers. So then you can change the values here and then save the atmospheric parameters, but in a reduced height range. So again, just be sure that you have the proper units here. And then as I'm preparing everything for running it later in parallel, you need a starting optical depth, although we are going to replace it, but you need a starting one. So in this case, I'm just defining a random one. I think if I go like this, yeah, it's an optical depth that it has the same points in height of the original simulation, but I played a bit with factors just to make it move from almost 1, log tau 1, to log tau minus 6, because I think this is more or less a reasonable height range that we could use for doing this in the synthesis. But I think this is basically arbitrary. What is not arbitrary, and I think Basilio can confirm now, is the optical depth at the highest point. In this case, I put minus 6, that is very close to the one that I am obtaining. But I think this one will really be preserved when you do the transformation. Right, Basilio?
Yeah, because this is used like a boundary condition in order to integrate the optical depth. Yeah.
Yes. So then the idea is that you can define an optical depth that it's not uniform, it has different values, but try to make the top boundary a value that you think you will use, like -5, -6, or something like that. And because this one will be preserved for later. So I mean, when you do the transformation, the final point will be -6, for example, in this case. Okay, then I define an array, a vector of 0, just with the same dimensions as one vector, because I'm going to save all the required atmospheric parameters for SER, and we don't know some of them, or we don't use some of them, like for example microturbulence or gas density. We will not use it. We will not use them now. So then I'm just creating this, and then I will show you how I use it later. And then the important thing is that this array is the one that we will save in the parallel wrap format. So then again is X, Y, meaning the horizontal domain, then optical depth, and then atmospheric parameters. Okay, and you have 11 here. So it means that we have all the parameters that are depth dependent, but the 3 parameters that they only have a value, microturbulence, filling factor, and stray light, they are provided separately. So in this case, we are just saving the values that are depth dependent. Okay, and then I just do a loop. I always have the same optical depth in the first item. Then I'm saving each pixel temperature. Then I put a note here that the second, so I mean the third vector of the SERV format is the electron pressure, but we don't have it. So because it's not provided by the simulation. So then we cannot put 0 there, because if not, the code complain. But the idea is that we are going to recompute it. So then the easiest thing to do is that, as we already have gas pressure, we can put gas pressure divided by 10. That is something similar to what we could expect by electron pressure. And then the idea is that the code will read it and will say, okay, I can start from here, but then it will be reevaluate it, and it will be compatible with the new temperature and optical depth that we will obtain. So basically, we cannot put 0 here, but it doesn't matter if it's not really the electron pressure, because we are going to recompute it. And then in microturbulence, we can put 0 because we are not using it. And then here is the atmospheric parameters that we have already formatted. So I mean, field strength, line of sight velocity, inclination, azimuth, and then here the height that we also tentatively define, and then the gas pressure, that this is provided by the simulation, and then gas density, and that we can also put a 0 here. Okay, so then with that, we
just one thing, the height should be the step side in the height should be right. You can shift all the heights, but the step side is important. Then you cannot define arbitrarily the height scale. Yes. Yes. Because the step side is important. Okay,
yes, that's true. That's true. Thank you. So I forgot to say. So yes. So then this X size is so I mean Z size is this one, the one defined here. Yeah. So if you picked the new simulation with a higher spatial resolution, so be aware that you need to update this one to 8 kilometers, and just create the high domain as again with a reference 0 that it will be just by eye, but with the proper step. Yeah. Thanks, Vasily. Okay, so then we save everything. I think we can just go like this, and then it will be very fast because it's only 250, and then we save it as a FITS file, and then the idea is that we already have a file that later on we will just run it in parallel. It will be the input of the program. We will do the transformation, and it will be very easy, and it will be completely parallel. So if you have 40 cores, you will run 40 pixels at the same time. And just to show you the temperature, so I mean the domain that we are going to test today is this one. So it's only 250 times 250 pixels, but you see some granulation and some magnetic field here. Okay, so then this one you will have in Dropbox, so you can check. If, for example, if you are running a Python program, you can check that the results are similar. Okay, so then I will move to the transformation, but just before going there, is there any question about what I have explained until now? Okay, so then let's go to the program. So this transform. So then I'm reading the FITS file that we have just created. Okay, and then I'm going to define here. I will explain you later better why we define it like this, but I'm going to define an optical depth vector that is uniform, and I pick these values. So just to show you more or less. So it goes from 1.5 log tau 1.5 to -6, that I think is a reasonable optical depth range for the computing photospheric lines. And this is the difference between 1 and the following point, and it has a step of 0.1, log tau 0.1. Later, we will talk about this, but I just define it here because for simplicity later. So then let's start with the dimensions. It's the one we created before is 250 times 250. Again, so we created before an array with the format required for doing the transformation in parallel. And now we are going to create an array with the format required for doing synthesis in parallel. So I mean, the previous one is for doing the transformation, and this one that will be the output, it has the same format that we need for running the parallel version of SER for doing synthesis. So I'm trying to do the things the most efficient as possible. So again, it's the same. So X, Y, optical depth, and the 11 atmospheric parameters that are height dependent. So in this case, we will run a loop. And what I'm going to show you now is how to do the transformation for the patch that we created in serial. So just in case you want to try it, or if you have a simulation that is not so big, then you can transform it in a few hours. Like, for example, the transformation of these 200 times 200 pixels can take around 1 hour. So if you have a field of view that is 500 times 500, then you can do it in serial while we are learning other things. And then you can use this program. But the idea is that for bigger field of view, or if you have a time series, it will be much easier to do it in parallel. But at least I will show you how I do it, how I did it before the parallel wrap for small snapshots, or with patience for bigger snapshots. Okay, so then I define an optical depth. The temperature is basically just, so the loop goes in I and J, so it's just picking pixel by pixel. And then so we have temperature, electron pressure, microturbulence, a field. So I just define what we need to just create an atmosphere in SER format. So this is what we have done in the previous classes. The only thing is that this Atmos is the one that we have just created from the MURAM simulation. Okay, so then we write an atmosphere that is called input.mod. And in this case, the optical depth that we are providing is some kind of random. And then let me put stop here. So then the idea is that we have saved one atmosphere for 1 pixel. And then what we are doing now is to call modelador 3. So then it's the same as before. So we have a control file, and then we are asking, in this case, modelador to run. There's an extra sentence because the program it's always printing things on a screen, and it's good if you are running 1 pixel, but in this case, we are going to continuously running 250 times 250. So just to avoid printing things in the screen, the code will print in 1 file. And then you will not see in the screen. So it's much cleaner. So then let's go to this control file that is a bit different from the previous one. It's much simpler because in fact, most of the things we don't use it, or at least I don't use it anymore. So the idea is that important thing is that you need an abundance file as before. So we are using the same. And then you have an input model that in this case is the initial MURAM pixel. And then you have an output model where you are going to save something. And in this case, what you're going to save is that if you go down, 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 and you go to this line, it says, if you are picking number 2, then you are starting from geometrical height and gas pressure, and you are computing optical depth and electron pressure. So then what we are going to do is we are giving an atmosphere. We are telling the code that please use the geometrical height and the gas pressure and also temperature, and provide the optical depth and the electron pressure. So it's very simple. We don't need to change anything here. Okay, so then if we run this one, so just let me go like this. Okay. Where is the stop? Okay, I think already computed. So we can go to the file. So we are using input and we are reading tau. Okay, so then you can see that input is this one. So this is optical depth, that one that we provided. And the new one, you can see that now goes from 5 and then it's changing a lot. And then it reaches -5 and then goes to -6. So then this is what I said, that the top boundary will be preserved and basically the others are more or less continuous. So then the code has changed this optical depth and also it has recomputed the electron pressure that here, for example, the first value was 10⁵ and now it's a different value. Okay, but sorry, I'm changing too fast. But for example, temperature, you will see that is the same. Okay, so then the code is recomputing basically optical depth and electron pressure. Okay, so then we have already transformed transform 1 pixel, and the idea is that if you want later after the class, then you just run it for all the pixels. But this is one transformation, and I put it a note here. The idea is that after that, I read the atmosphere, this output, and then you have all the atmospheric parameters. And there's an extra step that we need to do. So the idea is that we have geometrical height that is uniform from the simulation. So I mean, each difference between pixels is 16 kilometers. So then the resulting optical depth will be non-uniform because it's like that. So then for SER, what we need is an optical depth that is uniform. So then we need now to take all the atmospheric parameters that we have already computed and interpolate them to a uniform optical depth. That is the one that we will need for using it in SER, for doing synthesis in SER or design.
Just not anymore, but older versions require a uniform optical depth grid. Yes. Not anymore, but in any case, it's more sure to do that because if you have a very big step size in the optical depth, you will generate some uncertainties and some inaccuracies in the integration.
Yes. The current version doesn't support the non-uniform optical depth, but Basilio has a new one that it's in principle it allows it, but it has to be tested.
You don't have the okay.
The one
I
I'm
thought
sharing,
you was
okay. No, because the one I'm sharing is the one I have been testing a lot. So the other one I hope that we can test it thoroughly.
Okay.
In the next month, and then we can share it. But I think in principle it will be simpler to just use the output. But the truth is that in general you try to do things with synthetic profiles, and for example, if you do inversions and you want to, and there you have to do with uniform optical depth. And the idea is that then you want to compare. So for example, you said, I want to compare how is my temperature or my magnetic field at log tau 0. So then it's better if you already did the synthesis with a uniform optical depth. So then it's easy to just do plots or do comparison. So I think you are not losing anything, or at least the test I did between uniform and non-uniform, you didn't lose anything in terms of accuracy, and you have more flexibility later for comparison. Okay, so then I'm just interpolating to a uniform grid. In this case is the optical depth that I defined before, so the one that is defined here. So it goes from 1.5 to -6, and we are just interpolating it. And then I'm just saving the atmosphere in the format that we can use later for doing the parallel synthesis. But you can then just take one pixel here and write it like this one, and then you will have a pixel that you can use for doing synthesis.
I have a question.
Yes.
Can I ask?
Yes. Yes.
You generate tau like a parameter, but in reality it has to correspond to some wavelength. Where the wavelength is defined?
It's 500 nanometers.
Okay.
Yeah,
And
it's
in the continuum, obviously.
Yes.
Okay.
Yes. Yes.
Good.
Yes. Yes. It's because SER will always work with that continuum wavelength for inversions and for synthesis. So we just generate this one.
Oh, yeah, clear.
Okay.
Thank you. And when you integrate through line, also you change the optical depth there. How do you integrate? You also do Rabinian for each wavelength position when you do it integration in a geometrical scale. How do you do that?
No, in fact, you are integrating in optical depth, in continuum optical depth as a reference, but there are several procedures, but normally we are using Hermite procedure to integrate the related equation, and it takes the continuum optical depth at 500 nanometers as a reference, okay, and then it calculates the matrix, the opacity matrix. And then implicitly you are working with optical depth at each wavelength, but you are using as reference a continuum optical depth at 500 nanometers always. Yeah.
Yeah, it's normal. It's usually the ratio, of this. Yeah, exactly. But then it's not equidistant again.
No,
that's what I'm asking. Yeah. So and then you have to again interpolate it to equidistant scale? Or?
No. Hermite method is using an internally interpolation because it's working with a 4-order polynomial between 2 points, but it is doing interpolating the source function. In fact, not the optical depth, but it is considering that exactly the source function is like a 4-order polynomial between 2 points every 2 points.
Okay, thank you. Yeah.
Okay, thank you. Okay, so then I was saying that
only one thing. The Modelador 3 is a very old program, but produce as an output a lot of information that maybe you can, in some cases, you can use, like the sound, the speed of sound, the sound of the speed of the sound. I mean, some specific height and all the gradients, adiabatic gradients, and so on. A lot of information, and you can, if you are interested of thermodynamics of your simulation, you can use that because it's a lot of parameters, thermodynamical parameters.
Yep. Okay, so then I just show you that if I click here, there's a stop somewhere. Okay, so if I run, just 1 second. This, okay, so it's going to take some time, but you can see that it's relatively fast. So again, if you want to just compute 250 times 250 or maybe 500 times 500, you probably can do it in any computer in 1 or 2 hours. So if you want to give it a try over the weekend or next week, just run the program. You can use the same snapshot or create a new one, and you can see that it's relatively fast. So it will not take more than 1 hour or 2 hours. So, but in this case, as for the class, I'm just jumping it. I already did it. So let's compare how it looks. The temperature at what I assume was geometrical height z equals 0 with the temperature that we have computed at log tau 0. So I mean tau equal 1. So then okay, so then I read these. And then I will plot these. Okay. So this is the temperature, the original one, and this is the one in optical depth. So the first thing is that you see that it looks similar. So granules here, they look the same. You see that the pattern, I would say that here the contrast is not the one that we usually have in observation. So I would say that this is more or less more natural for me, that I usually work with observations. So, but in general, we can say that it's working okay. Later, we will see other things. And later I will also explain that there's some wavy pattern here. So in fact, I put here a note. So there's a wavy pattern or something. And the idea is that I have some ways of trying to improve in it, but I think it's something related with the simulation itself. I put it here a reference from Mark. It's already in the Dropbox file. So they already show, so this is 2010, and this is when they showed continued intensity at 500, so basically what we have done today. And you can see, let me make it a bit bigger. So there is also the same pattern. So I think it's not really related what we have done, it's something related with the simulation. But the truth is that I think here it was more, stronger than the one that we have now. So I think the simulation has been improving, and in fact the test I have made, and we will try to do it later on in the course, with the high spatial resolution one, basically I don't see it, the wavy pattern. So I think it's maybe related with the resolution of the simulation. So I will not be worried about that. I think the method that we are using is working. And also I think in this case we are using an optical depth step of 0.1, but you can go to something like 0.05 or even 0.01, that is 10 times larger. And usually it also gets attenuated. So you see less wavy pattern. But the truth is, yeah.
Sorry, Carlos,
yes.
Sorry to interrupt you, but I see it with RH too. So I really think it is a problem
yes.
of the
yes.
simulation. I think Matthias indicated that it might be a problem of the grids not being, for different parameters, not being on this, exactly on the same point. Or
yes.
they're slightly shifted. And
yes.
that's the problem.
Yes. 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 No, thank you. So the idea is that first of all, I think it's not related with our computation, but I think the most important thing is don't feel too bad about this, because the first one is that without changing anything, I already ran the continuum with those results, and it looks like this. So here what I'm showing is, this is the temperature in geometrical height, this is the temperature that I have just shown you, and this is the continuum at 500 nanometers. So you can see that there's still something, but it's much less important. So even if you see it in the atmospheric parameters, the impact on the Stokes profile will be smaller. And again, just changing the optical depth step will help. And definitely the high spatial resolution one, I don't see it. So it's just something that maybe was this run or something like that, but I will not feel too bad of seeing this. I think there's a question.
Hi, Carlos. Yeah, I have a question.
Yes.
I'm sure you explained that, but I missed that somehow. So you calculated the optical depths from the simulation, right? But in your input atmosphere, where you have that 11 column of depth dependent input parameters.
Yes.
There is no opacity, right? So how optical depth is calculated? I mean, is it calculated somehow from electron density and gas density or gas pressure?
I think Basilio is already nodding, so Basilio, you can answer.
Yes, internally, the program is evaluating the opacities. Yeah, you only need to give the abundances, and the program will evaluate all the opacities. The problem is that to know how many ions do you have, you need to solve the Saha equation, and Saha equation depends on electronic pressure, and you are providing gas pressure. Then you need to evaluate electronic pressure to know how many ions you have, and then to know how many electrons do you have. Then you need to solve an iteratively procedure. This is the reason you need to provide an initial guess of the electronic pressure. Then with the initial guess of electronic pressure, you evaluate such equation, you evaluate how many ions do you have, how many electrons do you have, and to iteratively have the electronic pressure. Once you have that, with electronic pressure and temperature, you evaluate opacities of every element that is important for the continuum. Okay, as you are going for hydrogen, H minus, etc. And with everything, you have opacities. With opacities, you evaluate, you integrate optical depth. Yeah.
I see.
Mm-hmm.
Thank you.
Bye.
Okay. Is that procedure described anywhere, written down? Because I feel like I would need to.
Yes. We're using, I think that the oldest is in Mihalas, and Mihalas a very old paper that is around in the 60s. I don't remember pretty well, 67 or something 67. Like. And later we are using subroutine that was written by Axel Wittmann. And in the paper of Axel Wittmann in the 74 are some description of that. Later, I have repeat the description in the SER paper. Okay. But maybe in the Axel Wittmann paper, I think is 74 is in detail.
Basilio, maybe we can look for the papers, download them, and put it in Dropbox for everyone.
Okay.
I will look for I will look for them, and then I will discuss with you. And if I find them, then I will put it in Dropbox, so then we can check it.
Okay. Yes, I think this is the Axel Wittmann paper. Other the Malip description of G. Dolandi has some information that is always interesting, and the SER paper. Okay, but we can upload that.
Yes. I will look for them, and I will check with you that they are the ones, because I think I have both, but just double check, and then I will put it in the same folder of today's class.
I have a question.
Yes.
I still don't get why you said about the waves is related with the step, because here you're showing the continuum, and in principle, if we are here in LTE, we are just kind of mapping the temperature to, I mean, here the temperature and the continuum, they look different, and we should not be mapping one to, or similar one to one. And why to form the continuum is the step is important. I got confused in that part, because you said that the problem might be in the step of the simulation, but I don't understand here from the radiation point of view, why is it important here, since we are in the low tau surface.
Yeah, I think the truth is that I don't know what is the. So you mean you're talking about the wavy pattern that appears in the simulation?
Yeah, exactly.
I don't know. The truth is that I don't know. I don't see it in the Bifrost or Mancha simulations that I have used. I don't see it. So I believe it's something intrinsic related with the code, but I don't know what it is. What I can really tell you is that with the high spatial resolution that I will provide a small snapshot in the future for doing tests, there you don't see that that pattern doing the same transformation. So I mean, doing exactly the same process, you will not see it. So I don't know exactly what they change between the low resolution and the high spatial resolution, but it's something that I see in this one, but not in the high spatial one. But I cannot tell you what it is.
And why it looks so different between the middle panel and the continuum panel? They should not really look very, very similar? Or it's just a contrast, just plotting?
No, maybe because the radiative transfer is erasing, I think, is smoothing the map, because you have a map like that. This temperature at log tau equals 0, and then over layers over this, I suppose that this step wave are diminishing, and then when you integrate all the temperature, because the continuum at 500 nanometers has mainly the main information comes from log tau equals 0, but it has all over the upper layers also have a contribution, and the radiation in some way is erasing this small fluctuation. I suppose.
Yes. Yes.
Okay.
Yes. So
Thank you so much.
okay. So yeah. So oh, okay, Jana.
I have a question. Maybe it's silly, but I don't know. Why are the two temperatures so different? Isn't the log tau equals 0 what we usually take as the zero height, right? While then you have Z equals 0 and you have like 3000 Kelvin more. So what am I missing here?
Yeah. So well, Basilio, I think.
No,
well,
I
okay.
suppose there is
No,
a
it's
Wilson
because-
depression.
Yes.
Okay.
Yes. So I mean, so here it's a fixed geometrical height, but depending on the conditions, for example, magnetic field, the photons that will escape will come from different heights. So in this case, I'm just picking one layer of the simulation, and so the optical depth here will be changing. And in this case, the optical depth is one layer. So then the geometrical height corresponding to this optical depth will be changing. So imagine that I have a sunspot here. So then the optical depth 0 will correspond in the umbra with a geometrical height of, I don't know, minus 800 or something like that. While in the quiet sun could be, I don't know, 100 or something like that. So I think is that we are plotting different things. So I don't know if I'm maybe
Yeah. Well, remember. So typically, height 0 is referred to as the average, where the average height where tau equal 1 at 500 nanometers. But remember that Carlos in the beginning, the leftmost plot, he just took a kind of a random by eye height that looked good to him.
Okay.
And then later after the tau was calculated, then you basically redefine what is height 0. Height 0 is not physically defined, it's by choice, right?
Yes.
Okay, so his original choice was off by a bit, because I mean we got 3000 Kelvin difference in a quiet sun. We're not talking about the Wilson depression. I don't think that.
Yes. But also the temperature contrast at one geometrical height is much higher than at an optical depth equal 1 surface, and this is because the H minus, which is the main opacity, is more or less self-regulating.
Okay.
Yes.
Thank you.
Yes. Okay. So then, before going ahead, the main message is just that I think this wavy pattern is something that we see, but I think you can use it this simulation already if you want to do tests or if you want to do studies, because I think it's not a big problem. And if you don't want to have it, there are some ways, as for example, increasing the optical depth when we do the interpolation before doing the synthesis. Or I think I haven't found it in the new one, in the high spatial resolution one. So maybe you can use a snapshot with higher spatial resolution, but still you can use this one already. I think this is not a big problem.
Yeah, I've also found that if you smooth it by 2 pixels, you lose a little bit of resolution, but at least you get rid of the pattern more. So if it bothers you, that's one way. And I think that's yes. But that's a clear indicating that the grids are maybe a little bit off.
Yes. Okay, so then, and I think the last one I have here. Okay, no, I think this was the last one. No, this one. So this is just something, just trying to more or less illustrate. So we started from this one. Again, this is a random selection, so maybe it's not the closest one, but it's more or less somewhere. And then this is how it looks in optical depth. So this is the temperature, line of sight velocity, and then you have magnetic field, then inclination and azimuth. So they look more or less similar, but now we have everything ready for doing the transformation. So then my advice here is that you can do these plots for checking that your results are more or less consistent, so if they look similar, but after that point, I usually don't go to this row anymore. So because you are going to start from this one, you are going to do synthesis and you want to check the spectral response to what is happening here. So then you work on this one. And then if you are doing inversions, you are going to compare the results from the inversion with this one. So then just keep this in mind for double check, but then basically you will work with this one from now on with any simulation that you use, because this is the one that you will use and you will use as a reference. Okay. And I think that's all today. Just let me check the program. Yes. And again, you can try, you can download the slab, that is the smallest one, not the biggest one, and high spatial resolution, and then just take 200 times 200 pixels from one corner. There you have granulation, and try to run the same program. Be aware that you have to change some things, like here the step size and the vertical step size, and also the height domain. It's going to be like 190 or something like that. So it's bigger, the high domain. So you can your relative z equals 0 will be in a different point, but you can run it, and there you can check if the new computation, the optical depth, so I mean the temperature in optical depth 0, if it looks better. And my impression is that in my case it was much better. So I think you could do it as well. Okay, so I think I have not forget anything. Yes. So then let me go to here. So then just try to run the test, or as I said, download the high spatial resolution and run it. Try to transform some pixels. Sometimes I have get an error, and when the code compute the optical depth, sometimes it's wrong. I think it was something like this. So maybe it's just 1 pixel or 2 pixels if you pick 250 times 250. So, but if you see it, then you should remove this pixel. I will show you how I do it when I do the computation in parallel. But basically what I do is that the pixels, mainly in the high spatial resolution, they are so similar between one another. So if one pixel is wrong, just replace it with one close to it, and it will be fine. But just in case if you get it, then just try to remove that pixel and just go from there. Again, if you have time and you want to really play, then just use the program and do the transformation for a bigger field of view. But if not, don't feel the pressure to do it, because I think soon, in 1 week or 2, we will do it in parallel. So then, okay, I think Saimi is asking if someone had trouble downloading the simulation. So did anyone download the simulation recently? It seems yes. Okay.
I'm also having problems to download it now.
Okay. Maybe there's a problem in the server. If not, we can contact them just to check if there's a problem. Okay. So then, okay, it's good to know. Okay, then let's wait 1 or 2 days, and if not, I will send them a mail just to check if there's an issue, and then they can solve it. Okay, so then what I was saying, we will do it in parallel, and it will be much easier. We will do it for a piece of the high spatial resolution, because it's in parallel and it will be much faster, and then we will see how it looks. The Stokes profiles for some pixels, you can make synthesis, as I did for the continuum, so you can pick a few of them. But again, we will do it in parallel. And yes, next class, I'm still thinking what we do in next class. I think I will probably cover finally how to compute, or how SER computes that. But as it is the same for desire, I don't know if I will do it now or later. But the important thing is that so when we started with the parallel wraps, we started evolving them. So first we had one that was working with SER for synthesis and inversions. Then we added the option for transforming the atmosphere. And then we added the option for computing the spin functions in parallel. And in the meantime, I was always working with Ricardo on different things. And at the end, we had like several versions of the Python wrap that they could do different things. And Ricardo said that he wanted to have a master version that can do the same, but without replicating the programs. But he's working on it. So I think next week, I will explain how to compute the broadening coefficient with collision with hydrogen. And after that, we will work on the parallel version. If we have the master file that Ricardo is preparing, fine. If not, we will work as I'm working right now, that is fine. And then as he is improving it, we will just move to his version. But the idea is that I want to give him some time, and collisions with hydrogen are very important, and you can use it in most of the codes, and we will use it in Desire. So I think it's good to learn how to do it next week or in 2 months when we start with Desire. But after that, we will start with the parallel wrap with either the master version, if Ricardo finished it and I had time to test it, or if not, with the versions that I have, that then we will move to the master one. Ricardo, do you want to add something or not?
No, it's just in principle next week it should be. It's almost done. I need to test it again to see if some bugs is always something.
Okay.
But in principle next week should be already.
Okay. So then I will test it over the next week, and then in 2 weeks we will start with it. Okay. So then next, yeah.
Carlos, could you open with an editor the .th of the model name?
Okay. So,
to show the thermodynamical parameters that is evaluating, and you can.
Yeah, this one.
Yeah.
Yes.
It is always is writing in .th.
Yes. Yes.
The thermodynamical parameters.
Okay.
With any editor, yeah.
Yes.
Because it's asking. Okay, this is the pesomet. This is Spanish. Okay, is this the mean molecular weight?
Yes.
Okay. It is. Then is electronic density, proton density. Hydrogen density, proton density. Okay, and then the degree, the ionization degree. And this is alpha is the compressibility factor, the derivative of density over temperature. And no, this is the delta is the derivative of density over temperature, and alpha is over pressure, is compressibility. Okay, this is dilatation compressibility. This is CV is exactly. This is a specific heat to volume and pressure, the speed of sound, and adiabatic nabla, and the total nabla. This is the logarithmic derivative of temperature over pressure. Okay, and then maybe in some cases this is in each row, if each the optical depth, the evaluated optical depth, the final, the resulting. Okay, then you have your model. All these thermodynamical parameters evaluated for your model. Normally you are not reading that, but in some cases it is interesting to have some alpha delta for some calculations. Okay.
Yep. Okay. So I think that's all from my side. Again, as I said, next class will be next Friday, and probably I will try to explain you how to compute the broadening coefficients due to collision with neutral hydrogen. That is, it's used all in CERT, RH, and Desire, and I think most of the codes that do inversions also. So I think it's very good that you know at least how to compute in normal conditions, because some transitions are a bit special, but normal transitions, I think it will be easy for you to understand how to do it. Okay, so is there any question or comment regarding today's class?
So is the line optical depth calculated in the same way, Carlos, as it was described by Basilio, or it is somehow calculated with easier way from simulation, for example, from line opacities?
So you mean if you want to do a synthesis with the simulation?
Yeah, line synthesis.
It will be the same as we did in the first class or the second class. So you have to provide an atmosphere to the code, and then the code will solve the Saha-Boltzmann equation, and then it will integrate the source function, and so it will be the same process. So the idea is that what we have done today is prepare the atmosphere in the format that SER requires. So we started from a format that it was completely different. We adapted, computing the optical depth, and now you have the atmosphere in the same format as the FAL-C model or the HSRA model that I put in, I think, in day 1 or day 2. So we just did a transformation for feeding SER. But the idea is that the process will be normal. So like you do a synthesis with the code, you have to solve everything. But yeah.
Internally, the SER code will evaluate LT opacities, solving Saha and Boltzmann equation, and this side is using RH modules, and this is evaluating also background opacities and line opacities, considering the population of all levels and so on. Then, but this is for later when we speak about how to synthesize a line. We will speak. If we are working in LTE, it's easier because we are just the population as Saha and Boltzmann equation, and RH we will need also to take into account the different change of population because of radiation. Okay.
Yes.
But
the idea, Vasily, is that with the format that we created today, we can also run this side, because the code only needs these 11 columns that we have, the depth-dependent 11 columns, and then from there it will feed anything that is happening inside, and it will generate a profile, or it will embed a profile. So what we have done today is just create a cube that contains atmospheres that are in the same format, same units and everything, and that the ones we need to use in SER.
Yeah, just preparing the input files for SER or DECIDE, because for DECIDE is the same, as the same input files. Okay.
Yes. Okay. More questions? No? Okay, so then thanks everyone for attending today, and I hope to see you next week. And as always, if you have questions, just write them in Discord or even by mail, or just next week you can ask them. Okay, so then thanks a lot, and see you next week.
Thank you.
Thanks, Carlos.
Bye.
Thank you. Bye. Bye.
Thank you.